Hello there. In this lesson, we're going to look at the law of partial pressures and partial volumes and some applications of that around the chemistry lab. This here is called a bell jar, and we can use it to change the gas pressure in and around a substance, and we'll have a look at what happens in there. And this here is called a gas collection tube, and so you can see it's sealed at the top here. And inside you've got some liquid there, it's water, and some bubbles that are coming up to fill this part with the gas. So both of these involve gases and mixtures of a gas under different conditions. We're going to look at how that relates to this law of partial pressures. So in this lesson, we're going to be looking at mixtures of gases, and gases mix really well, and each gas will contribute independently of the other gases to the volume and the pressure of the mixture. The volumes will add up. If you know the volume of one gas and you know the volume of another gas and you add them up, you will get the volume of the mixture once they're together. And that's because of that independent nature of gases not sticking to each other or influencing each other when it comes to the volume or the pressure. So as a mathematical relationship, you can say that the total volume is equal to the sum of all the partial volumes. Once this is in there, you can think of the part that was, nitrogen taking up 4 liters of the space inside this balloon, and the oxygen would take up the 1 liter, and so overall you're going to end up with 5 liters of the mixture in this balloon. And so those are called partial volumes. So partial volume, partial volume, and 5 liter would be the total, right? So the same relationship exists for pressures as long as the container is of fixed volume. If you have some nitrogen in one container and you have some oxygen in another container and you combine them into a third container or into one of the other containers, you will get a pressure that is the sum of the individual pressure of these gases. So if this is like 0, 1, 2, 3 units of pressure, and this is 0, 1, 2 units of pressure, well then this one should be 0, 1, 2, 3, 4, 5 units of pressure. And that is because these partial pressures will always add up to the total. Same as with the volumes. So one place where partial pressures or partial volumes show up in a lab is when you're collecting gases over water or some other liquid. And that is due to vapor pressure, so gases that are the result of evaporation of that liquid. So in this gas collection tube, you have the gas that you're collecting, maybe some hydrogen from a reaction, but there's also some water vapor in there as well that is just evaporating off the top of this surface of the water in the tube. And so the amount of vapor pressure that you could get would depend on the liquid that there is there. So water is the standard one there, and water has that pretty strong intermolecular attraction of hydrogen bonding. And so the vapor pressure of water is fairly low compared to some other liquids that you might use. So here is hexane. It's got 6 carbons, and it has a much higher vapor pressure because a lot more of it will evaporate at the same temperature. So that vapor pressure will depend on the temperature of the liquid and the surrounding gases. The weaker the attraction, the more vapor pressure you will get. So another neat thing happens when you change the temperature. Eventually you get to a point, as you know, at 100 degrees Celsius, when the vapor pressure will be the same as the surrounding pressure. If it was under standard conditions, 760 millimeters of mercury, that's standard pressure. And once you get to that point, the water would boil. That'll happen a lot earlier with this hexane. If you warm it up, you get to 760 a lot earlier, maybe at 70 or 80 degrees Celsius, and it would boil. The opposite is also true. If you lower the atmospheric pressure, which is what's happening in this bell jar, if you lower this atmospheric pressure down to, say, 17 millimeters of mercury, well, then that's the vapor pressure of water at 20 degrees Celsius. So if you got 20 degree water down here, then it'll boil. It'll change to a gas at a lower temperature due to the low pressure that's around. Now this is sometimes an issue if you were doing something at an altitude. So mountain hikers might take some food to cook and eat along their way up in the mountains, but water might not get very hot before it boils because of the lower temperature that exists up at the top there. So you might not be able to cook food very effectively, at least not with boiling water. Now, equalizing the pressure inside of a tube is also important for many studies of gases. And a neat way you can do that, even in a high school lab, is using a gas collection tube like this one. And what you do is, if you notice, if you have a cylinder with the tube in it, if you push it down under the water, you'll find that the water squishes that gas into a smaller volume. And likewise, if you take it up above the water, it'll expand and go to a greater volume. So what you want is to be at the level of the water, at the same water level inside as outside of the tube. And at that point, you'll know that the pressure inside equals the pressure outside, because the two water levels represent an equal amount of pressure pushing down on the surface of the water. So we use that oftentimes to work out the pressure inside of a tube, where you could never get a little pressure sensor in there, but as long as you have the water levels the same inside as outside, if you know the pressure outside, then you'll know the pressure inside. Alrighty, so here it is all together. If you want to collect and determine the number of moles of gas in a gas collection tube, there's a couple things you need to do. First of all, you set up your reaction and make the gas. In this case, it's hydrogen. This here is a little piece of magnesium, and it's bubbling away making this hydrogen gas. Well, up come the bubbles, and you know you've got hydrogen in that space at the top of the tube. The other thing you have there is water as well, right? Because the water will evaporate in there, and so you'll have both of these gases in the tube. And the pressure will be due to the combination of both of those in there. So knowing your vapor pressures and being able to look them up for water is really important when you're collecting gas over top of that liquid and over top of the water. So oftentimes, if you got cold water, it might be at 15, 12.8 millimeters of mercury out of whatever that total is going to be due to the water. And then you know that the rest is due to the other gas. In this case, it's hydrogen. Alrighty, so let's apply what we just learned. We know we're collecting hydrogen gas here over water. The pressure outside of the tube is 760 millimeters of mercury, and it's at 20 degrees Celsius. So we know, because this is collected over water, that there's some water vapor in there as well. Since it's at 20 Celsius, we can look on our handy table and see that 17.5 millimeters of mercury of that total is actually water. And so we got to take that away. So we know that P total equals the pressure of the hydrogen plus the pressure of the water. And to get to just the pressure of the hydrogen, we're going to have to subtract, right? So we got the total pressure minus the partial pressure of the water. And so that's 760 millimeters of mercury for the total, and 17.5 millimeters of mercury for the water. And so the pressure of the hydrogen is going to be 742.5 millimeters of mercury. And then you can move on now that you have gotten rid of the effects of the water. Now, a common partial pressure, partial volume type of question is this two-chamber system with a valve in between. And let's say we've got 5 liters of helium on one side, and it's at 65 kilopascals, and we've got 5 liters of argon on the other side, and it's at 42 kilopascals. Well, if you open this valve, then this argon is going to go that way, and this helium is going to go that way until they're all mixed together. You should end up with a new pressure of the total, right? Now, because they're both expanding means the individual pressures of these gases are going to decrease. And that's going to follow good old Boyle's law. Remember, P1 V1 equals P2 V2. So we want to know P2 for both of these. So it's P1 V1 divided by V2. And so it's pretty straightforward. This is nice, easy numbers. We got 5 liters and 5 liters, so the total is 10. So the pressure we're starting off with for the helium is 65 kilopascals in 5 liters, expanding into 10 liters, and so we're going to end up with half that pressure. So that would be 32.5 kilopascals. And then, so that was the helium. And then we got to do the same thing for the argon. And the argon is 42 kilopascals in 5 liters divided by 10 liters. And so you're going to end up with 21.0 kilopascals of the argon. So then it's pretty easy. You just add them up. Remember that the P total equals the partial pressure. So we got P hydrogen, or helium, sorry. And then we've got the pressure, partial pressure of the argon. So that would be 32.5 plus 21.0 kilopascals, which gives us a grand total of, what is that, 53.5 kilopascals in this system. Alrighty, hope that helped. I'll see you soon.